Go ahead. All right, yeah, probably good time to start. So it's my big pleasure to introduce Ilya Gruzberg, who is visiting us from University of Ohio in Columbus.
Ohio State.
Ohio State. Columbus. So Ilya received his PhD from Yale. I want to say 97.
98.
98. Okay.
Close
Next on the postdoc at Santa Barbara, and this was followed by a professor position at the University of Chicago. But then Columbus, Ohio came and seduced him somehow to move to Columbus, and he was resigning to Eros in 2012, something like that. And Ilya is very well known in his works in mathematical physics, borderline mathematics, sometimes disordered system, quantum politics, and many other interesting subjects. So today it's quantum gravity. Please.
Thanks, Alex, for the introduction. So I was going to, well, as we go along, you'll see what I mean, what I'm not going to say. But first of all, let me thank you for inviting me here. So I remember that this place used to be called place of 10,000 lakes and very few weirdos. And I hope it's still the case. But what I'm trying to say, I hope I don't disturb this balance by coming here. So I'm not creating a lake or I'm bringing in a weirdo with me. So anyway, so this is going to be indeed a sort of a rather mathematical story, but it starts with physics nevertheless. So let me start. Used to work just now. So what's going on? No. Okay. Something is not working. So let's see. How about now? Yeah, now it's working. Good. So right. So let's remember this story of the integer quantum Hall effect. That is an old story. You take a two-dimensional electron gas, you expose the strong magnetic field, and you observe this fascinating trace of resistance and Hall resistance. So the quantized plateaus, incredibly accurately quantized. This is all beautiful. And so there's a lot of universality here related to topology and localization. And that explains why this kind of beautiful story can be seen in something as ugly as this sample that is shown here. There's also another kind of universality happening here, which is controlling the behavior between the plateaus. This is one of the quantum Hall transitions that is a well-known Anderson transition. And the quotation marks here stand for the following reason. So it's been known that it exists, it somehow is something interesting to look at for a long time, but we still don't understand it in the sense that we don't have any predictive power scheme where we can extract universal properties of this transition from theory. Only numerically we can access it so far. All right, so this is what I'm going to be focusing on, right? So this region where you go from one plateau to another. So the simplest description that you can think of just neglects completely the interactions. You start without any interactions. So it's a single electron in a magnetic field in the presence of disorder. So U of R is a random potential. So without the disorder, you have lambda levels, equally spaced. Then when you introduce the disorder, it essentially broadens the levels, makes them into lambda bands. But more importantly, what it does, it localizes pretty much all the states in the system. Single particle electron states are localized, except at these energies where the lambda levels used to be. And so these states are extended in a certain sense, not quite, but they're not localized for sure. All right. And then you can vary your Fermi energy or magnetic field to cross the chemical potential. When it crosses one of these extended states, you get a step, new step. You go to the next step. All right. And so what we believe is happening is that the localization lengths of these localized states diverges in a power law fashion as you approach these critical energies. And this is described by some universal critical exponent that is analogous to critical correlation length exponent in conventional phase transitions. So in fact, there's lots of analogies with conventional phase transitions, but there are also quite profound differences. In any case, so this is a continuous phase transition happening in the quantum system, and what we want is to be able to explain its universal properties. Extract
These components of its exponent can be measured experimentally.
Sorry?
Are you suggesting that this exponent can be measured experimentally?
Yeah, okay. So this is this is what I was going to maybe let me do it. Oops, not this way. Let me go to the slide that I have as a backup. Indeed, it can be measured, or with some caveats. So let me maybe explain to you what's being done here. So this is the same trace I was showing, except now it's magnified. You only see one step, one transition in 2 steps. And what people do, they do this scan along the magnetic field axis at different temperatures, right? And you see that at high temperatures, this step is pretty broad. As you lower the temperature, the step becomes sharper and sharper. And somehow the slope of this step signifies that some divergence is happening at 0 temperature, right? And in fact, these traces intersect at a single point. So this is exactly where the critical magnetic field is. And you can collapse them into a single curve by a single parameter scaling, essentially, right? And what you can do, you can, for example, what they do practically, they take the slope of these lines as a function of the magnetic field and plot them as functions of the log of the temperature. Log of the slope as function log of the temperature gives you a straight line, and that gives you some exponent that, well, naively is a combination of the dynamical critical exponent z and the population exponent. So for a long time, nobody could disentangle these two. So all experiments were reporting this product here, and it was pretty consistent over the years, always more or less the same. So in a tour de force, people managed to cool the system to single millikelvins in a dilution fridge in Florida. And then what they saw, they saw that this whole thing rounds off, right? And they attributed to the phase coherent lengths at this temperature being of the order of the system size or exceeding it, right? So then the whole thing becomes phase coherent, and then you see this rounding off because it's a finite sample. And so what happens is that they managed to cut samples of different sizes from the same wafer, so nominally it's the same system, right, but different sizes. And now they were able to find the scaling of this temperature, this temperature, as a function of system size. And that gave them access to Z separately from everything else. So they claim that Z is up 1, and then you get me. So that's the experimental status of this story. Yeah. It is tour de force. And so this is 2009. Many subsequent experiments on this transition happened in other systems. So this is traditional gallium arsenide story, but you've seen it in graphene and many other systems. So this guy is steady. I mean, pretty much everybody reports the same number. In fact, even though this such detail has now been repeated in any other system. All right. So this is this is my tribute to visiting physics department. So no more physics will be in this talk. So all right. So now I'm switching to theory completely. So I wanted to also point out that this is something that you would be interested in the context of a regular magnetic, let's say, transition or something else. In Anderson transitions, there's a lot more interesting stuff going on. In particular, if you think about the structure of the wave functions themselves at this point, they're very interesting. There happen to be self-similar random multifractals. So they look like this. So you see, they are not localized. You see some peaks that look like localized wave function, but then you go away and there's some smaller peaks at a different scale and some other peaks somewhere else. And this picture is sort of self-similar. You zoom in, you'll rescale things, you'll see the same thing again. So this multifractality, so superposition of fractals of different scaling properties, is an intrinsic property of this kind of critical points. Okay, it's not something that you see in regular magnets. And multifractality is very interesting for various reasons, but also for people who care about interacting systems. Effects of interactions in such a system would be in particular governed by matrix elements of the interaction in such type of states, right? And so that leads to all kinds of interesting enhancements of various quantities. Yeah.
So what actually plot is that?
It's wave function intensity, psi squared, absolute value of psi squared. All right.
Is that continuous spectrum of scaling exponent?
Yeah.
Related?
Yeah, absolutely. Like the whole continuum of exponents should be discrete.
If you throw envelope into this peak, the envelope is gives you localization value.
But there's no envelope of that type. It's not exponentially localized. That's what I'm trying to tell you. It's not. So, okay. At this point, no. I mean, I don't think so. You go away, then you have, so localization length at this point is infinite. Okay. It's already diverged. It's exactly at the critical point. We're sitting exactly at the critical point.
Critical point.
Yes, it's a critical wave function, not localized.
No, critical is infinite, right?
I can tell you a lot more about multifractals, but it's not my focus today. Okay, it's I mentioned it because the
Maybe just answer
Yeah.
Boris' question. So that's all at the critical point.
yeah.
If you move slightly away from the critical
Yeah.
point, then what you start seeing envelopes.
Yeah, so yeah, that's right. Until you go very far into the localized regime, then you just see a single peak, pretty much a single state, right? Okay. Any more questions to that? Good. So I wanted to mention, just from the theoretical point of view, single particle disordered Hamiltonians can be classified using their global symmetries, and that classification done by Altman and Serbauer tells you that there are 10 different symmetry classes. And this has been then miraculously used to classify topological insulators as well. So it's an interesting story how this is related to classification of topological states as well. But so for me today will be important that there's an analog of the integer quantum Hall effect in a completely different context. You can ask what happens to quasi-particles in superconducting states in the presence of disorder. And those quasi-particles can localize and delocalize and can be transitioned in the quasi-particle transport in superconductors. And that's described by this spin quantum Hall effect and thermal quantum Hall effect transitions. All right. So unfortunately, this whole story is very complicated. And the reason we don't really understand what's going on, because there's no small parameter. It's not a theory where you can do any controlled perturbation theory. All right. And so just from general approach to this story, if we believe that this is a critical point in 2 dimensions, it has to be described by some conformal field theory with C equals 0. But which conformal field theory and how to extract anything from it, we still don't know. Okay, there are lots of work here in various aspects of this story. What I'm going to be focusing today is on this one. So random networks and quantum gravity. There's a whole bunch of papers here. And the tool that I'm going to be appealing to is the Chalker-Coddington network model, which is a standard model which is supposed to produce some results for this transition. So this is how it's been constructed. So Chalker and Coddington were thinking about a picture of the electron moving in a strong magnetic field in the presence of smooth random potential. So imagine you have random potential whose scale of variation is much, much longer than the magnetic length. Then the states more or less look like the drifting orbits. The electron sort of goes along the potential lines of the potential, right? So if you draw a topo map of this potential, then these lines are the electronic states. And they are quantized because of Bohr-Sommerfeld quantization, semi-classical, okay? And so what you do, you start filling this landscape bias states from the lowest energies to highest energies, and they form these puddles. And in the beginning, when you have very low energy states, they are completely disconnected. They're very, very far apart. It is totally localized. Then you start changing your chemical potential. The puddles grow. They start to coalesce, right? And at some point, you can bridge the last gap between the left-hand side, right-hand side, and at this point, the transition happens, so to speak, from the insulating state to the quantum Hall state. Now, view this in this picture. This looks like percolation, so it does remind the classical percolation transition, and in fact, the original ideas behind this picture suggested, so the original papers suggested it might be just the classical percolation transition. Of course, people then realized that not everything is so simple. So Chalker and Coddington in particular said, okay, let's try to numerically simulate the story, but to be able to do this, we have to simplify it a lot. We have to sort of place the saddle points where the interesting quantum mechanical effects may enter. We place them on a regular square lattice, and then we can apply transfer matrices or whatever to the system. We can simulate it numerically. Okay, and so they did it. They estimated this exponent nu with some big error bars. It was around 2.5 plus minus 0.01, 0.1. 0.5, sorry, they had very large error bars at that time. And so this was a pure matter of convenience. You cannot simulate it using transfer matrices, this kind of random story. So
I should mention that classical value is 7/3.
Classical value is 4/3. 4/3.
Yeah.
That's right. And then there was this story about adding +1. That's right. Good. So this is the more or less.
That one which enters kappa, which gives kappa is 7/3. Kappa is 1/7/3.
No.
3/7.
No.
Kappa is 3/7.
No. So right.
42.
Close to. No, you're right. It's close to. That's correct. So let's backtrack. So that number. Oops, I have it on this other slide. Okay, I can write it. I can write it here.
You either use the
Kappa is 1/z mu. If z is equal to 1, then kappa is 1/nu. And so if nu is 7/3, then kappa is 3/7.
which is 0.42.
Yeah. So let me say what experimentalists tell you. The experimentalists tell you. So this latest experiment where we had 2 decades in temperature to get the slope actually. So they report 2, 3, 8 plus minus 0.02. I don't know. Take it or leave it. I mean, that's their reports and result, right? So this one, 7/3 is 2, 3, 3, 3, 3, 3.
Okay. At this level, I cannot count.
Right? Okay. So, but anyway, so this is the story about 7/3 is nobody believes it. Okay.
Yeah.
Just sort of like, maybe slight digression, but so, when we look at quantum Hall plateau transitions in these like semi-conductor heterostructures, there's a lot of disorder, and so
Yes.
it makes total sense that you would start with a model that's kind of. I was curious, if you look at like the graphene sample, like
Yes.
with Andrea Younghead,
Right.
I mean, these ones are super clean. Is
Right.
there any indication of the nature of the transition?
So, well, okay. So one disclaimer is that I honestly can say that I don't really know, but maybe to see this, you have to disorder it intentionally. I don't remember what people have done there, but they report the same exponent. That's what I remember. I remember that it's a universal thing, right? So there must be some disorder, otherwise you wouldn't see it at all.
In real samples, you don't see integer quantum Hall. Everything is fractional.
But even for the fractional, you need disorder.
Plateaus practically disappeared. Everything got fractional, so that's different issue.
But to see even fractional plateaus, you need disorder. That's a statement without disorder. You cannot see any plateaus whatsoever. Just by Galilean invariance will be a straight line, right? So yeah. All right. Okay, so now this is the sort of the status of the things in recent years. So numerics has been evolving, and so the most recent, there's much more recent data as well here on numerical simulations of this Chalker-Coddington network model, and pretty much agrees that it's in the 2.6 range, as opposed to experimental, which is 2.38. Right? Not a big difference, and maybe it's not such a big deal, but it is different, right? So this is the graphene experiment that you know. So okay. Well, so there are lots of caveats here. So even in the interpretation of experimental result that I was showing to you, there's some very subtle issues that need to be addressed. Simply because the when you present some scaling result, then there's something t divided by some t characteristic t of that sample, right? There's some dimensional number that has to be divided by to get the scaling. And the claim is that these characteristic temperatures could be different for different samples. But it's all murky. So in some sense, even experiments have to be interpreted with some care, as pointed out by.
Why is it a better form? Just the scaling of number.
That's right, but they have to. So you see that those experimental traces, they come from different samples. They superimpose them to get a straight line. Again, how this happens? Yeah.
So it's not like same sample, different
No, yeah. To get this long straight line, they have to superimpose several times. Yeah. Anyway, so so the discrepancy between numerics and experiments, in my opinion, the most likely explanation is that we don't understand the role of electron-electron interactions. So in fact, it's known that if you start with this non-interacting critical fixed point and ask whether interactions are relevant or irrelevant, there's a clean answer. If they're short range, they're irrelevant, and if they're long range, they're relevant. So depending on what you do in your sample, can you screen your Coulomb interaction to make it short range? I don't know, but certainly if they're relevant, then we have no say whatsoever about what's going to happen. Just totally open. All right.
But they may be relevant for Z, and for Z,
Yeah.
Coulomb means interaction means Z equal 1 by definition,
That's right.
and the rest.
But
is
you
not.
know, but what's interesting, so I'll come back to you just in a second. So the thing is that another story is that there's no unique Z exponent either, because you can look at the scaling of the dephasing time, decoherence time, phase breaking. I mean, all kinds of scales exist, and they may have different scaling with temperature in principle. So that
about this.
so okay. Anyway, so you had a question.
Yeah, so this experimental arrow there of nu seems remarkably small. Like,
Yeah.
percent or even better.
It's only in that paper that
So what you showed
yeah,
earlier, that seems hard to believe.
yeah, it is hard to believe. Yeah,
And then there's the uncertainty on the dynamic critical exponent.
sure,
I
absolutely.
guess that shouldn't be smaller than one.
And so this paper is pretty much the only one that does this. The plot they show for the one I don't have here, for how this rounding of temperature scales with the system size, well, they have 3 points, straight line through 3 points. Okay, and they say Z is equal to 1, but they are, in some sense, I think they are spoiled by theorists who tell them that Z must be equal to 1. Right.
That's the problem.
So they say, okay, they believe everybody who's saying that the quantum critical point controlled by the Coulomb interaction, Z must be 1. So they say, okay, so we confirm, right? Yes.
And sorry, I think you said it before, but the calculation of this sort of being relevant or irrelevant, what field theory is used?
So, right, well, it's not a field theory. So it's a numerical simulation. You essentially have to say that let's look at so you need to compute some expected. So more or less, that's what I was saying in the beginning. You have to compute the matrix elements of the Coulomb interaction in the exact single particle states, which are this weird multifractal states. And the scaling of that quantity with this will give you whether it's a relevant or irrelevant prediction. Right? Good. All right. So what our contribution to the story is that we came up with an additional mechanism that can actually change the critical properties, even in the non-interacting picture. And that's what I'm going to tell you about. It's the geometric disorder story. So namely, if you go back to this, how the Chalker-Coddington was created, well, you look at the actual profile of some random potential and you go around the puddle, and there's no guarantee that there are 4 settle points around it. There could be any number of settle points around it. And so it's better maybe to think about structurally random networks of this type, where the only constraint is that at every node you have 2 in and 2 out. But otherwise, the connectivity can be anything. Okay, so that's what we want to study. And so we have to include now the average over the disorder. Into the average of disorder, we have to include the summing over different types of random graphs. And so this is very similar to how people used to do what's called the discrete models of two-dimensional quantum gravity. Okay, so the first question is, can we do anything with this, numerically or analytically? So the first attempt was pure numerical. I mean, doing anything with this kind of system, I don't know how to. But what we came up with, we started with the Chalker-Coddington and randomly picked some fraction of the nodes and started opening them, making them completely transparent this way or that way. Okay, and once you do this, let's say here, if you focus on this part of the lattice here, there used to be 4 squares. Once we open this up, we get 1 hexagon and 2 triangles. So, and if you keep doing this, you can get all kinds of polygons this way. You still can do the transfer matrix here, and you can do some other approaches as well. And interestingly enough, you just numerically simulate this guy, and you came up with the for the particular value of this fraction of the nodes that we open, we get the number that is agrees with experiments. Most likely it's a coincidence, but nevertheless, the interesting story is that the exponent changes. Okay, and later people did scan this P, and they have a whole seemingly a whole line of fixed points with different mu's. That is not really understood. But the fact that this exponent changes from 2.6 to 2.4 with high precision, this is a high precision numerics, right?
But this for P equal 1/3.
That's right. Yeah.
The P is equal to 1/3.
What's special about P equals 1/3?
Yeah.
Nothing. So again, my co-authors, so R. Sidrikan believes there's some special thing about 1/3. I don't know what it is. So I don't believe.
Jumps is in the air.
This guy?
Jumps is
No, this is actually pretty easy to understand, because because when you open all the nodes, right, then it becomes a classical percolation problem, but you cannot really tune the transition anymore to see it. It's the only this critical this variable, the knob that you turn to go through the transition, just disappears in that problem at all, and that effectively seen as the
Here, rapid changes around 1/3, right? 1/3 is the minimum, and then the very rapid.
yeah.
So
Well,
again, same
Yeah.
question. Why
I have no clue.
some special point?
Yeah, possibly, but I don't know. And the reason I don't know is because this system does not have any analytic approach. I mean, I don't know any tools to approach it. Okay.
so this is the authors. This authors.
Yes, this is the numerical paper of this. So in our original paper, where we came up with this story, we only did 1/3. Just did
By
1/3
chance.
by chance. Yeah. Yes.
So in this picture here, when you get rid of the nodes, you're always making pink bubble?
No, you can, oh, well,
Or is it?
no, you can open this node vertically. No, you
You
can,
spoil the
it's both.
You spoil them. 1/3 spoiled, right? 1/3 change node.
So
No,
actually 2/3. So 1/3 you take open horizontally and 1/3 vertically.
Right, so.
So it's a lot of nodes are
I
now
saw.
scrambled. Yeah. All right. So now you see I have this question here about Harris criterion. So when we publish this, the most severe criticism we hear from people is that what about Harris criterion? So let me explain to you what's going on. So Harris criterion is a famous criterion in the study of disordered systems, which tells you that if you have some critical point whose correlation length exponent and spatial dimension, when multiplied, if this product is bigger than 2, then bond disorder added to this critical point cannot change its critical property. It's a famous criterion, but it has some limitations. Let me just right away. By the way, so if we believe this, we take the 2.6 multiplied by 2, we get 5.2. So it's certainly very much bigger than 2. So how can anything we add to this point change its nature? Well, so let me hand waving at least. So first of all, bond disorder is a special type disorder. You can have other types of disorder in your system. Bond disorder specifically tells you that you have this knob that goes across the transition. There's an operator that is attached to this knob, right? And then the coupling constant multiplying this knob is what's becoming disordered. This is called the bond disorder. In the easy random bond Ising model, that's what it is. It's literally J's within the spins become random. That's what it is. Okay. And then also this is a perturbative result based on the central limit theorem. So you have to have. You can only obtain this result if you're dealing with distributions that are narrow in some precise sense. The central limit theorem doesn't work for all distributions. Only works for some narrow distributions. So that can be violated, and then we don't really know what's going on. All right, so this is what we believe is happening here. So in our case, when we have this random graphs, the corresponding disorder is strong in the sense that it violates the central limit theorem. But in any case, so this is hand waving and just trying to defend ourselves from this kind of criticism. So it would be nice to have a solvable example so that borrowing joke from Shankar. So if you do so he defended the exact solutions, right, which many people don't care about. But he said, if you have an exact solution, then you're protected from people who come to you and say, what about the Teller effect? So that's what I want to say. I don't want anybody to approach me and say, what about something? So this is
to understand a little bit. So are you saying that the disorder you're thinking about can't be modeled as like some local random potentials, or are you saying that it's long range correlated, or are you saying both?
Let me try to answer it partially now, and then later I'll make another comment about this. So the feature of these random graphs is that the types of these random graphs that were studied a long time ago in quantum gravity context were dynamical triangulations, where you just try to create a surface by gluing together triangles. And the trick they use, they say, I can glue as many triangles as I want around, and so in some sense, local coordination number is a very broad distribution. It can be very large, thousands, right? So then, in that sense, local temperature, which is, in mean field sense, right, can fluctuate a lot. So that's the. But there's also coordination is also a possibility, or some correlations in this thing is also something that I'll mention. Right. So what I wanted to say is that now we have as I mentioned, there's some cousin of the integer quantum Hall effect. This spin quantum Hall effect in class C of Alton and Sternbauer, and it's described by another network model. But what's nice about it that it can be mapped exactly to classical percolation problem. Okay, so you can map this problem to classical percolation. There's some technical steps that do it, but then you can get localization length exponent just from known properties of percolation transition. So now for this transition, it really is 4/3. It's related to some thermal exponent. And there's a lot of more exponents that can be extracted from what's called multi-Hall operators. In particular, many multifractal exponents that I mentioned can be extracted from this mapping as well. So it's some nice example where you have some analytical tools to handle this non-trivial transition. Okay, and so what we do now, we try to place that spin quantum Hall on a random graph and see what happens. So now let me tell you sort of a brief history of this thing. So if you look at just triangulations that I mentioned here, the dual to the pi cube Feynman diagrams, right? So if you have Feynman diagrams with triple vertices, cubic vertices, then in large expansion of this action with phi cube, you'll get diagrams of that type. And so that's what people did. They essentially can, what you have to do to consider in the planar diagrams, you have to do a matrix field theory. You have to write a matrix integral, and then expansion of this matrix integral will give you this kind of structure in large n limit. Okay, and then on top of this, you can place some physical degrees of freedom, like the Ising pods or n spins on this thing and solve them. The critical points can be solved on these dynamical objects exactly, essentially. There's some set of tools that you can use. All right, now let me just tell you what this is. So what is drawn here is an example of such triangulation where you have to remember the following. So when I try to draw these things, to be able to draw like a vertex where you have, what is how many? 1, 2, 3, 4, 5, 6, 7 triangles come in. I don't distort anything, but in reality, what you have to think about are equilateral triangles that are glued this way. So if you try to glue equilateral triangles this way, you will inevitably be the paper will be bumped, right? So you'll have the conical singularities where you glue less than 6 triangle. That will be spikes that come out of this surface. And when you glue less than more than 6 triangles, you'll get a monkey side. So you have local places where the curvature is negative and places where the curvature is positive. And so in some sense, you have a surface which is very much distorted. And this is what you get if you really try to embed it into 3-dimensional space. It's very weird configurations like this appear. People call it quantum surfaces, quantum suit, whatnot. All right, and this whole thing is just one member of an ensemble where you have to sum over. So our disorder now includes summing over this kind of stuff. Okay, and what is known from the classical works of various people is that critical exponents of transitions of the usual Ising, pods, percolation, whatnot, on this kind of dynamical lattices differ from those on the plane. They're really different and analytically accessible, but different. Okay, and so what connects the planar geometry on this fluctuating story is the formulation of the quantum gravity in terms of a field theory that was done by Polyakov and collaborators. And that gives you a relation between the dimensions of the operators, scaling dimensions of operators in the plane, and scaling dimensions on the fluctuating surface. So there's some exact formula that for specific value of the central charge looks like this. So it's not very complicated, but nevertheless, if you know the planar story, you plug it in, you get the gravity story. And if you know the gravity story, you can extract the planar story. Both ways, right? And so it's extensively tested against exact results from stat map models on random graphs. Okay. Now, in our case, it's very similar, except that our type of graph has never been done before. It's not very simple. It's not a dynamical triangulation. So what you have to think about is how does percolation work here? So more or less, the shaded plaquettes represent the electronic puddles, right? And so opening a node this way would allow the electrons to go from one puddle to another. And so that's modeled by drawing a line between the points in the middle of these lakes. And so if you only keep these purple lines here and dots that sit in the middle of the lakes, you get a pretty complicated structure. It's not a very regular graph. The coordination number is different at every point and so on. So it's not easy to study this, but so nevertheless, we have to study percolation on this kind of graph. And we can do that, and that's where the Kazakov's contribution. So you were asking what already. So he told us how to do this essentially. So he knew how to handle this story, and so it can be solved using the same matrix techniques that used to be done in the 80s for more regular dynamical lattices. And what we get is this result. So we used to have, again, nu used to be 2.6. Dimension of space was 2. Now these weird objects in quantum gravity actually have fractal dimension 4. They cannot really be even embedded in three-dimensional space. So that picture that I was showing you is some approximation that's not really working. So these guys are really high-dimensional objects. And the only thing that you can extract from this story is a product of these two guys. And so you see that if you define nu tilde this way, then it's 1. So it used to be 4/3, now it's 1. So it's definitely different. So it's changed. And you can also extract other exponents, as multifractal exponents and Hall exponents. They also turn out to be different from the planar geometry ones. It's slightly different technical process, but nevertheless.
And what's the meaning of this exponent?
This guy?
With this and
Yeah, so in percolation, this is sometimes called watermelon exponent for the following reason. Imagine you have 2 points in your system, and you look at percolation clusters that come close to 1 point, and the same clusters come to vicinity of another point. This configuration has rather low probability, because you have to, so in some sense, you draw a vicinity of a point and say, okay, there's n percolation clusters that almost touch that point. They're separate clusters, right? You can draw the boundaries, the halves, they become loops in a sense. So you have n loops over here, and the same loops have to go all the way to this other point and approach it there. So that configuration has a probability that decays as 1 over r to this power. Okay. And so this power is different, but so that's a percolation exponent. But from this mapping, it can be related to wave function exponents for the multifractal wave function. That's a second study. Okay. What I was trying to tell you is that, again, some explicit solution of that specific model confirms that this relation does hold, and we can explicitly check it. So if you started with 4/3, then the thermal eigenvalue, thermal dimension is this, 5/4, it's delta 2, and then you plug it in here, you get 3/2, and by the scaling relations, you get 4 out of it. So, and these guys also go into each other upon this thing. So So what I'm trying to tell you here is that the geometric disorder that we introduce violates Harris criteria. So even for spin quantum Hall transition, the exponent is 4/3. If you multiply it by 2, you get 8/3, which is bigger than 2. And so according to Harris, nothing should happen. But nevertheless, we change the exponents, and that's in this case, nobody can argue with this. It's an explicit calculation, and everything is done very carefully. Okay, so so you were asking about the correlations. So this is the slide that is relevant here. So another interesting story is that Harris criterion has been extended to some random structures. So the person named Luke was interested in quasi-crystalline kind of things, and so he realized that in this case there's some correlations between the various things on such kind of lattice. So he introduced what's called a wandering exponent beta, and in the Harris criterion, which focuses on some large volume and looks at fluctuations of the local transition temperature using central limit theorem, there's always square root involved in the central limit. So in Harris, there's 1/2 coming from the central limit. So this exponent beta replaces this one essentially. So it sort of tells you the scaling of the fluctuation of some local transition temperature in a large volume does not obey central limit, but has some other scaling exponent. Maybe because of the correlation between the exponents. So that's phenomenology is in this beta. It's a phenomenological exponent you use there. You can then study it numerically with various lattices and whatnot. But then the criterion changes to this kind of stuff. So so numerical simulations of this random quantum gravity surfaces tells you that this beta is 3 equals some result like this. And so if you plug in 3/4 here, you get 1/4, and our result is 4 here. So we seem to be exactly on the verge of this thing. So we seem to be saturating this bound, and it sort of suggests that maybe we've indeed have flown to the point where we just saturate the appropriately modified inequality for disordered exponents, the Chase-Fisher-Spencer inequality. And one final thing that I want to say. So again, my collaborators in a separate paper have done this numerics for trying to find this beta for the type of models that we originally simulated. So you start cutting these things and creating these random networks. And well, for whatever it's worth, they report that beta is close to 1, equal to 1. So if beta is 1, then any disorder is relevant. Okay? Anything that you put should be relevant, because it's 0 on the left hand side, so it never. So it somehow they say, okay, that's why everything is flowing when you change things. And so, but again, this is numerics, and they were doing it in the context of the usual Chalker-Coddington, where we don't have an analytical theory. So I don't really know what's going on there. All right. One last thing I want to.
Maybe from one you wouldn't ever expect any person.
Yeah, it's something. Yeah. Again, so this is. I wish I understood it better, but push that on. Yeah. So the last thing I want to say, which is probably for me, it's a very important lesson that in this, even in this older story of when people were doing it in the 80s, they realized that quantum gravity actually buys you a lot. Namely, the two-dimensional Ising model in a magnetic field cannot be solved on the plane. There's no solution. Ansager only works without the magnetic field, right? So you can only extract this exponent beta from some scaling relation, not directly, okay? At the same time, quantum gravity allows you to solve this problem even in the presence of a magnetic field. So it gives you more information directly, right? And so that's what Kazakov and Bulatov did. And later, Duplantier showed again that if you have some complicated problem, so he was doing all kinds of geometric stuff. So you can imagine Brownian walkers in a half plane that you start them somewhere, they go, and you ask, what's the probability that their paths do not intersect up to some scale? It's a very complicated problem. Mathematicians have been struggling with it for a long time. But then he said, okay, if you do the same story on a fluctuating geometry on the type of quantum gravity, things become much easier. You can solve them for free. Then you use KPZ relation to bring them back to the plane and you get some useful answers. So this whole series of papers where you were doing it. So the upshot is that if you have a difficult problem in the planar geometry, then you hope to couple it to quantum gravity. Maybe there the solution will be easy. And that's what we are trying to do now with the actual Chalker-Coddington, not the spin quantum pole, not the percolation story, but the original CC coupled to this randomness in geometry. And that's a work in progress, but we are very hopeful and do something. Yes.
Is the idea that easier because you're averaging over them?
In some sense, yeah, my intuitive feeling about this is roughly the following. So it's not exact, but it's pretty close. So remember that many phase transitions have upper critical dimension, right? Beyond which you become mean field and everything is known. So since the fluctuating surface has practical dimension 4, you're more or less working like that's my intuitive understanding of this thing. But it does liberate things. There's a lot less correlations between various things when you start fluctuating.
And this KPZ relation is that.
Yeah.
Yeah.
That's right, exactly. So suppose we can solve CC in this random way, then you go back by yeah, we should be able to get the two exponents this way.
What if the assumption is that going to KPC?
Right.
It doesn't do unitary.
No. So this story here, right? So this something hidden here, which is the central charge. I didn't write it here. So there's an analogous formula for arbitrary central charge, except there's a bound. So people don't know how to go beyond c equals 1. So anything c equals 1 or below, you can handle it. Below is above c equals 1, nobody knows what to do. So for that reason, for example, if you have some kind of field theory, like West Zemina or something where the C is bigger than 1, nobody knows how to couple it. That's the only constraint that I'm aware of. Right. So thank you.
All right. We've got many questions, anything else? Yeah.
Any chance to do anything with the document?
Well, okay. So Boris will probably answer it better than I can. The point is that
You did the elections in 1950.
yeah, that's right. So the thing is, let me put it this way. So the real experimental systems always have instructions, and I envision that theoretically you can do two things. You can say, let's first treat disorder, then add interaction as something we can hopefully do after that. Or you can say, let's ignore disorder, do strong interactions, maybe understand something about strong interaction system, then add disorder to it. So both ways are theoretically nice ways of doing things, but my underlying physics is purely disordered physics. So once you do this, then you can make statements of whether interactions are going to change your critical behavior or not, based on just this criterion of relevance or irrelevance. That can be. So I think this is under control.
It is perturbative relevant.
Yes, that's correct. That's correct.
But do they see that the interaction is weak?
Yeah.
You put it on top of.
No, it's not the weakness that is important. It's the range.
Exponent will change.
It's not the strength, it's the range that is important.
Okay. So, but there are so long range interaction and what is
Relevant.
relevant,
It's certainly relevant.
and you.
And the
change-
borderline exponent is like 3 or something. So it's a Coulomb is certainly way relevant.
So you can get any exponent between 2 point
Problem.
B and
Yeah,
B and.
But then when it's relevant, so if it's irrelevant, then you say, okay, maybe there's some non-perturbative, it can still screw things up. But when it's relevant, there's no, I mean, I don't know how to handle anything. Like, it's a strongly interacting critical point. I have no clue.
You mentioned several times that central charge is 0.
Yeah.
Why can't it be?
So this is a very simple, technical but simple statement. So to handle these other averages, you have to either replicate your system or do the supersymmetry, right? In either way, your final partition function is equal to 1. And therefore the free energy is 0. So it doesn't scale with anything. That's why the central charge is there.
All right, anything else? If not, then let's thanks.
Thank you.
Мне сегодня уматывать, да?
Да, ну, понимаешь, у меня глупая получилась ошибка. Мне нужно было приехать вчера поздно, а
Да,
улететь завтра.
да.
Ну, вот как-то, видишь, вот я... Сори. Так получилось.